Good afternoon. I'm Tim Williams from Argonne, and I'll be talking about our apps readiness program and our newly announced system. Just, if there are those who don't know about the LCF and how it's distinct from NERSC, for example, the Leadership Computing Facility, there are two sites, OLCF at Oak Ridge and ALCF at Argonne. And our mission is capability computing. So a relatively small number of very large projects who require some significant fraction of the machine for single runs. These two main Insight and ALCC computer time grant programs you've probably heard of. An important point about the LCFs is that the facility and these time grant programs are open to the world, essentially. It's open to not just DOE or government labs, but also academia and industry. It's not restricted to US investigators or projects either. And we are agnostic to the funding source for your research, which you're asking us for computer time to support. Our only main caveat is that we expect the projects to produce publishable results. So that doesn't mean your code has to be published, or your data has to be published, but just some scientific results. So with those guarantees, we've had some good success in having industrial participants in our programs. Our current production system is Mira. Mira is an IBM Blue Gene Q machine. It's 48 racks, each has 1,024 nodes, and each node is a 16-core PowerPC A2 chip. It has 16 gigs of memory per node, giving us a total of about 3/4 of a petabyte of RAM. The peak speed of Mira is 10 petaflops. We have two sort of mini-me versions of Mira as well that we use for different flavors of testing and debugging and for discretionary applications. Tukey is our analysis and visualization cluster. So it's based on AMD CPUs and NVIDIA Tesla GPUs. It mounts the same parallel file system as Mira, which is a 28 petabyte GPFS parallel file system. So it's well set up for analyzing results from Mira. So what's coming next at ALCF? We are in the process of acquiring our next generation system through the Coral collaboration, which Cherrick mentioned briefly, but I'll just say a bit more, that this is a collaboration among Argonne, Oak Ridge, and Lawrence Livermore National Labs. We put out a call for proposals with the purpose of procuring 3 systems in 2017-18 timeframe, and with the peculiarity that we plan to choose 2 winners from the proposals. And those 2 winners, in addition to meeting the requirements, also must be architecturally distinct from each other. So that's a sort of charge that we have from DOE to maintain these distinct architecture tracks, at least between the 2 LCFs. And the way it worked was OLCF picked one architecture, Argonne picked one architecture, and Livermore was free to choose either one. So the Oak Ridge architecture is what Cherrick was just telling you about for Summit. And Argonne's system, which is named Aurora, is what I'll be telling you about next. And this is the other architectural track. I'll also be telling you a little bit about a machine called Theta, which is a smaller scale interim machine. So our chosen architecture out of the Coral procurement is built by Intel and Cray. Intel is the prime contractor on it. They'll be providing the chips. It's a homogeneous, many-core, self-hosted system. So in that way, it's a fairly natural extension of what we're used to with the IBM Blue Gene system. It has about the same number of nodes as Mira, our current system. But with that node count, it's 18 times faster than Mira. And it does that while still maintaining less than a threefold increase in power consumption relative to Mira. And Mira was already a fairly power efficient machine. It rated highly on the Green 500. So things are improving there. It's an Intel architecture, which kind of goes without saying here. So just a few more details, essentially what we're allowed to tell you today. So the peak of this system at the base configuration will be 180 petaflops. We have options to bring that out as high as 450 petaflops, given some infusion of scalable dollars to procure something like that. The processor will be Intel's third generation Xeon Phi chip. This is codenamed Knights Hill. The number of nodes for the baseline system will be something a little over 50,000. The platform it's being built on is Cray's Shasta platform, so this is sort of beyond XC. The total memory in the system, incorporating high bandwidth on-package memory, much as Katie was talking about with Knights Landing, local memory and non-volatile memory will aggregate up to 7 petabytes for the baseline system. The interconnect will be Intel's second generation OmniPath architecture using silicon photonics hardware. We'll have a burst buffer, which will be based on Intel SSDs, and that's also hooked into the OmniPath fabric. The file system will be a Lustre file system, which is new to us, and we'll start out at about 150 petabytes. And we should see with that greater than 1 terabyte per second I/O bandwidth. The peak power consumption of the whole thing will be about 13 megawatts. And we'll be taking delivery of the hardware in 2018 for a production startup time in 2019. So I'll be talking about how we're going to make the transition to the new system, but first let me just put up a timeline here. So what you see is in blue is Mira in production. And what you see in purple on the bottom row is production for Aurora. Now, the red arrow is indicating what had been our planned end of life for Mira. And that's the point where our support from IBM runs out and the machine will probably start to atrophy, if not fail in a more comprehensive way. And when you're running a center like ours, you really want to have the opposite of this. You want to have an overlap of production with your new system with continued production of the old one. And so what we're doing in part to accommodate that is, procuring a system called Theta. So you can see here the orange bar is when Theta comes into production. We'll take delivery in 2016, production for that in 2017, and that will continue through the startup of Aurora. So what is Theta? Theta is also based on Intel and Cray hardware. It's also a homogeneous many-core self-hosted system. And it will be roughly comparable to Mira, which is aligned with our use for it as a Mira supplement and replacement in a gap, at about a third the power consumption. Theta will be based on the second generation Intel Xeon Phi, that is the Knights Landing chip. And Katie has already talked quite a bit about that, so I won't go into much detail, but this is what it is. And what's important for us at ALCF is that this architecture is the next step in the path to the Aurora architecture. So it's a very natural transition machine for us to bring our applications and new applications up to speed so that they'll be ready for Aurora. The platform here is the Cray XC series. And what we can say about these nodes is that we'll be getting somewhere above 3 teraflops per node, per Knights Landing node. And it will have something more than 60 cores, as Katie already mentioned. We're building our system with 192 gigabytes of DRAM on each node. And it will use the Cray-Aries interconnect. Part of the reason for putting more memory per node on this system was we'll be using it as a test bed and for some data-intensive computing projects. This will be taking delivery of in mid-2016. These are just more details about the chip. I think Katie went through just about all of this already, so I won't dwell on it. Just to underscore again the importance of this high bandwidth on-package memory, which can be stated safely to be at least above 400 gigabytes per second bandwidth. All right, so NERSC has NESAP, and Oak Ridge has CAR, and ALCF has the Early Science Program. This is our applications readiness program for our next generation systems. It'll be patterned after a similar program we hosted for MIRA, also called Early Science. And we think we really got a lot out of this program. Every project proposes a science campaign, and we got some very interesting new science out of these projects. We also came out of it with technical reports and public community presentations from the development teams on these projects about what they did and how they did it, getting ready for the next generation system. So these reports are useful information. I won't go through any details, just call out that we had 16 projects in that program, and these examples we see here are five of the different projects from the previous version of the Early Science Program. So it spans a lot of areas in algorithms and scientific domains, as does our production workload at ALCF. So the Early Science Program for our next generation systems, which is the ALCF3 project, will have two phases. One phase for Theta and one phase for Aurora. The Theta phase is smaller and shorter in time scale than the Aurora phase, and for that we'll be pre-selecting a few projects and then having an open call for proposals, which should be announced next week. Next Wednesday is the plan. And we'll choose another 3 or 4 projects from that call. We have funding for 4 postdocs to support these projects, so 4 of these will be able to hire on a dedicated postdoc who sits at ALCF but works very closely under the scientific supervision of the PIs of the projects. For Aurora, we'll have 10 projects and funding for a postdoc for every project. The call for proposals for Aurora Early Science will be coming out in 2016. So what are these projects? How do you apply? The proposal process we've tried to make relatively short and easy. It's kind of a light version of an insight proposal. So all the ingredients you might put in something like that go in here. You propose a scientific run campaign with it will be somehow high impact. You describe and demonstrate the parallel performance of your application today, and then describe in some detail the development that you'll need to do to get to the point of running that campaign on the new hardware when you get it. So that includes the porting and tuning activities is what we focus a lot of our thoughts and attention on, but also includes introduction of new algorithms or new physics, which can be done on today's machines, but is needed to accomplish the science you've proposed. The selection process will have a computational readiness review. It's very much as the review process that Tjerk spoke about. A review for the potential science impact, and an evaluation of the team to determine if we believe that the team is ready for what they need to do in a fairly short amount of time. We also, to the extent possible, optimize the choices so that we sample well the spectrum of scientific areas and algorithms and numerical methods that are in our production workload. In the selection process, as has been the case with NESAP and CAR, we will invite some participation from amongst our institutions and other stakeholders like the Trinity and Coral partners. This gives us some valuable insight, and it helps us in our task of coordinating and collaborating on these apps readiness projects. As I said, the announcement will be coming soon for the Theta Early Science Call for Proposals, and so if you watch this site, it'll be there in about a week. So what do we do to support these projects? This goes on a number of fronts. We mentioned the postdocs, and a member of our scientific computing team, the so-called Catalyst team at Argonne, will partner with one of these projects and help with preparing the code, but also in mentoring the postdoc on the HPC issues and performance. We'll be host to several different kinds of training, starting with training for the project participants directly from the vendors. This is explaining in detail under NDA, this is our hardware, this is our software, this is how you program it. And later on, at the point where we start getting early hardware, we'll host some intensive hands-on workshops where we bring the project participants in and really try to get somewhere on running and scaling the code on the hardware. The other thing we provide, of course, we're a user facility, so we provide cycles, and that includes time on our current systems for the kinds of development like new algorithms or physics modules that can be done there. Access to simulators as we can get them from the vendors, and access to small early hardware as well. Argonne has something called the Joint Laboratory for System Evaluation. So what they do is build little 1- and 2-node white boxes as soon as they can get a Knight's Landing chip or a Broadwell chip. And we'll provide access to these systems for our early science participants. And as mentioned before, something we think is critical to the success of this project is as soon as we have a rack on the floor that we can power up and get running, we hand it over to the project teams for the early science program. That was where a lot happened last time. Finally, the carrot for going through the pain of working on one of these projects is at the end of it, after we have accepted the machine and before we turn it over to the production users, there's a period of about 3 months which is dedicated completely to the early science projects. So they have essentially free rein on the machine and very large allocations of time to complete these ambitious science campaigns. This timeline just shows you a rough picture of how things flow. You can see the orange timeline is the Theta early science phase, and it ends just before Theta goes into production if you jump down to the production graphs below, and the purple is Aurora. And here I'm just indicating the points where if things go as they did with our last early science program, we'll be having these various kinds of workshops. All right. So as I think you've got the idea from what the other speakers have said, that we're actively talking to each other about these programs. And we are trying to coordinate as much as we can with each other. There are definitely already, and will probably be more projects which have projects in more than one of these programs, but that's a good thing in some ways, partly because we're trying to be advocates for portability and help bring the community consensus around some ideas for what we are going to do for portability. We've had a number of meetings as a group with people from our centers and others to talk about how we can coordinate these multiple efforts and how can we somehow help the project's program portably. We had a meeting in January with quite a few participants, so we brought in the vendors for the for the 2 tracks of architecture that Cherk was talking about, and had whole day sessions where they laid out their software roadmap and asked the vendors some of the same questions about portability and support for interlanguage calls and other details. And we had a good discussion there. It's not an easy problem. One of the things that's often mentioned in talking about portability with these new systems is OpenMP4, 4.x, which we will have, and in more than one compiler. And the reason it's mentioned, I think, is mostly because part of the effort in OpenMP4 came from an infusion of people from the OpenACC compiler directive for accelerators world, and that has resulted in the target pragmas for OpenMP4, where you can target data and computation onto an accelerator or multiple accelerators. There's also in OpenMP4 the SIMD pragma, and all of our systems, present and the next generation systems, will have compilers that do vectorization for SIMD type vectorization, and they all have slightly different directives you can use to assert that something can be vectorized, and this we hope will at least clean up some of that code so that at the source level you can express assertions about vectorization in a uniform way. So all of this is good, and we know that the users on the Intel Knights Landing, Knights Hill architectures are going to be using MPI plus OpenMP as their primary mechanism for programming the systems. And so in a sense, they will automatically be using OpenMP4 without the target directives. So source portability is useful in a sort of mundane way, but if you want performance, it's kind of a different story. So we're well aware and have discussed at some length now how and when one has to dive down the software stack into layers that are much closer to the hardware. And it's guaranteed that many of these applications will continue to need to do that. And in doing that, our only advice is really kind of apple pie, which is encapsulate that within libraries, frameworks, or code modules. And the sort of laundry list on the right of high-level interfaces you see, are try to represent several different approaches for that. If you look at Raja and Cocos, those are using C++ template metaprogramming and generic programming to provide a high-level interface above highly tuned for specific architecture implementations underneath. And the differences of the implementations underneath can extend not just from GPUs or CPUs, but also for the data structures, inverting structs of arrays of structs or structs of arrays. That can be done below a uniform high-level programming interface. And I'll stop there so we can get to some questions.